My colleague in the Astroparticle Physics and Cosmology Division at SKA Institute of Nuclear Physics. So Debasish, his main research interest is right now dark matter and its detections. So he is involved in various experimental aspect of it and as well as theoretical studies. Debasish will tell you about all those things.
So it's not morning, it's afternoon, I think. So good morning, good afternoon. And so the title is this: Radio Signal from Dark Matter in the Milky Way. So there are three things involved. One is Milky Way, of course, which is our home galaxy. There is dark matter and there is radio signal. So Milky Way, we all know, it is a spiral galaxy. It's a disk-type galaxy with a thickness of around 2 kPa, and where our solar system and many other galaxies are there. Anyway, so nothing much to say about that. There's a lot of things has been told, I think, in this Vigyan Samagam about this Milky Way. And there is dark matter and radio signal. Now, dark matter, as the name suggests, it is dark. That means it doesn't emit any electromagnetic radiation. So, what is the relation dark matter and radio signal? Okay, then I will try to explain all this. How can we get radio signal from dark matter? And then this is radio signal. Radio signal is one part of the electromagnetic wave spectrum. So let us go one by one. The radio signal can come from synchrotron radiation, and so I am just talk about synchrotron radiation a little bit, although I am sure you know pretty well of this. So this one already shown. So this electromagnetic spectrum, how it comes, it is simultaneous oscillation of electric electric field vector and magnetic field vector in a plane, and then it can emit waves of different frequencies, starting from a very high frequency, that is gamma rays, to the very low frequency, which is radio waves. And accordingly, their wavelength also changes, shorter wavelength and larger wavelength, because we know lambda goes as 1 by nu and all. So these radio waves can, today's focus is this part, radio waves. And radio waves can come from actually synchrotron radiation can be in the radio wave, this wavelength regime. So synchrotron radiation is what? So we all know that when an electron is moving in a magnetic field, it is accelerated and it follows a spiral motion in the direction of the magnetic field. And in the process of acceleration of the electron in the magnetic field, it emits synchrotron radiation or radio waves. To elaborate a bit more, again you see this is a more formal pictures. Here this is the magnetic field direction. The electron is coming and it will of course tend to be a circular motion. It is a spiral motion actually. If you solve this equation, you will get it easily. That is not difficult to find out that it will be a spiral motion. And then this centripetal acceleration will be the plane perpendicular to this B and V. And the synchrotron radiation will come out in the direction of this velocity, which is tangential to the circular motion. So with this, synchrotron radiation is something to do when an electron is accelerated in a magnetic field. So I have to have electrons or any charged particles for that matter in a magnetic field. Then only we will get synchrotron radiation, but how can we get it from dark matter actually? So that is the question here. And actually this synchrotron radiation or these radio waves can be detected by the SKA. SKA is built for meant for that. So this detects radio waves from the sky, from the galaxies, galactic center, or other places and all. Our focus will be actually the Milky Way, so mainly the galactic center and the other parts of the galaxy, from where somehow dark matter produces electrons, and that electron, by the influence of the magnetic field in the vicinity of the galactic center or the other places, they will emit synchrotron radiation in the radio wave, and that wave can be detected by SKA. So this is the idea. So that means SKA can also be used as a dark matter detector in the Milky Way or in the universe. Actually, dark matter has not yet been detected that way, in direct or indirect way. Only its presence has been known by its gravitational effect only. So with this, so magnetic fields in our galaxy, that's what I am saying. So somehow, somewhere dark matter is always there. I am coming to dark matter in a minute. Somehow the electron or charged particles will be produced. It is just like that it cannot be produced because dark matter, being dark again, it doesn't have any charge or anything, otherwise it would have been detected by now. So I am coming to that again. But if electrons or charged particles can be produced by some effect on dark matter, and that charged particles will then subjected to these magnetic fields at the galactic center or somewhere in the galaxy, and produce synchrotron radiation, means radio waves, which then, if possibly detected by SKA, then we can tell about something more about dark matter, or we know the nature of dark matter and all, which is all unknown yet. So with this, so again, this is the sort of mapping of the magnetic field of dark matter, magnetic field of the Milky Way galaxy. Again, so whatever charged particles that we are talking about that may come from the dark matter, that will be subjected to this kind of magnetic field, and then it will emit synchrotron radiation. That's the idea. So the question is radio signal from dark matter in the Milky Way. So one by one, what is dark matter? I will try to explain, because that's the subject very close to my heart, and then I will try to say how dark matter can produce electrons or charged particles, which, when subjected to the magnetic field in the galaxy, will produce in effect radio signal. So what is dark matter then? An unknown non-luminous matter with almost no interactions with anything else, any particle in the that we know, any known particles, except gravity, because the dark matter has mass, so it has to have gravitational interaction, and that is how actually the existence of dark matter could be predicted in the galaxy or in the universe. And some measurements indicate that more than 80% of the matter content of the universe. So matter content of the universe, more than 80% of the matter content of the universe, it is around 85% of the matter content of the universe is this unknown particle dark matter. So the budget, I will show the energy budget is that 4% only is the known matter, which we are all made up of, galaxies, galaxy clusters and everything. And around 25.6% is the dark matter, and the rest 68.3% is some other mysterious thing called dark energy. So the matter content of the universe is 31 point something percent. So out of that 25.7% is dark matter. So that's why I told 85% of the matter content of the universe is made up of this unknown matter or dark matter. And there are compelling evidence that they are all pervading across the galaxies, the galaxy clusters, galaxy superclusters all over the universe. And perhaps you know what are the galaxy clusters? Galaxies are actually a virialized gas of stars and other nebula and all. Galaxy clusters are are a group of galaxies which are virialized, means which are in equilibrium under the common gravity of all the galaxies, and that forms a group of galaxies which is called the galaxy clusters. And then superclusters is again the group of galaxy clusters those that are virialized, means that are in equilibrium with a bigger common gravitational wave field. Okay, so this is just preliminary idea of dark matter. That means since it does not interact with any of the known particles, its detection is very difficult, and its nature also very difficult to decipher. And of course, the common sense will be what? This dark matter should not have any charge, because if they have charge, they would have this electromagnetic radiation from there, and so one could have detected it. So they should be neutral particles. They most probably should be stable particles, because otherwise, if they are unstable particles, they could have decayed down to the known fundamental particles, and of course they do not emit any kind of radiation. So this is the first impression, knowing, just reading these 3 points actually. So that's what I was just mentioning that. So dark matter cannot be, and most probably not be, the known fundamental particles. So what are the known fundamental particles? I mean, I have put these particles at the backdrop of the CERN Large Hadronic Collider, where most of the particles are discovered, but this is not it is not the LHC where it is actually LEP and all other accelerators where those particles are discovered, but LHC actually discovered what? It discovered this Higgs particle. So this is the fundamental particle zoo known till date. That means this is the fundamental building blocks of nature, and this contains fermions. It is gone actually. So fermions and bosons. So fermions are again divided into 2 parts, which is the quarks and leptons. How they are divided, I am telling in a minute. And there are bosons, and bosons there are 2 categories. One is the carriers of the forces, which is the photon, Z boson, W boson, and gluons, and carriers of which forces I am telling in a minute. And then there is this Higgs boson, which is responsible for giving the masses of these fundamental particles. And then somebody says that all these masses we see here, it comes from the Higgs. This is a wrong statement, because Higgs gives mass only to the fundamental particles, the bare mass. But what we see here, this table, these things, whatever, our body, etc., are made up of proton or the nucleus basically. And in the nucleus, what is that force is acting? It is the strong force that is acting. So if you, nucleus is made up of what? A proton and a neutron. I am digressing a little bit, but this you should know that this is not Higgs which gives all the masses in the universe. So the masses in the universe that mostly given by these strong forces, and because of the following reason. If a proton actually has 2 up quarks and 1 down quark. This is U is up quark and D is down quark. And if you add the masses of this up quark and down quark, 2 up quarks and 1 down quark, that comes from the Higgs mechanism, from the Higgs, then it will be around, say, 30 MeV, 30 MeV, 30 MeV, 90 MeV. And 1 proton mass is what? 1 GeV. So you add those masses, 90 MeV, and proton mass is 1 GeV, from where this huge mass is coming, and that proton and neutron putting together in the nucleus, that gives all this creation, right? So that comes because they are strongly interacting through gluons, which is the force carrier of the strong force, and that actually gives the maximum mass to any object that we see, which are built out of these fundamental particles. Okay. So coming back to our discussion, here there are 4 fundamental forces in nature, which is weak force, responsible for the beta decay, which is weak means very weak actually, strong force, which is operating in the nucleus, inside the proton. I mean, these two up quarks and one down quarks are put together via the strong force in a proton, and the carrier of these forces are gluon. Carrier of the weak force is this W and Z bosons, and carrier of the electromagnetic force, which is another fundamental force of nature, is this photon gamma. And there are, of course, gravitational force, and this gravitational force is, of course, not included in this in this set of things, and these things are described by what is called the standard model of particle physics. And standard model of particle physics is a perturbative field theory, but it does not include the gravitation because there are complications in that. But those are other things, those are particle physics. I am not here to discuss that. But the point what I wanted to make here is that our dark matter does not belong, perhaps most likely does not belong to any of these fundamental particles. And one more thing I forgot to mention you, that these carrier bosons, which are called gauge bosons also, why it is called gauge bosons I cannot explain in this talk, but these are vector bosons in the sense they have spin 1. And in the known fundamental particles, only particle which has a spin 0 is Higgs boson. And that's why it is called a scalar particle. So only scalar in fundamental particle zoo is the Higgs boson. But again, coming back to our point is that these particles may not constitute the dark matter, except of course these neutrinos. These are electron neutrino, mu1 neutrino, and tau1 neutrino. These neutrinos, which are the leptons, and these leptons are only subjected to weak interaction. They do not undergo strong interaction, and electromagnetic interaction, of course, they will go if they have charge, like electron mu1 tau1, but neutrinos does not have any charge. So they do not undergo any electromagnetic interaction, and they also can serve the purpose that we defined earlier slide. What could be the dark matter? What could be possibly the dark matter candidates? Now, you can estimate how much percentage of neutrinos are in the universe, and you add together, it falls far low of that 26.5%. There's 26.5% of the total content of the universe has to be dark matter, and neutrino contributes to maybe 0.04%. So even if this serves as a dark matter candidate, they certainly not the whole realm of dark matter. They cannot contribute to the whole realm of dark matter. They contribute, but in a very minuscule way. So let us proceed. I mean, excuse me for a second. Now, why I put this photograph here? This looks a little irrelevant, but I put it purposefully because this dark matter I told everywhere. It is in the galactic scale, it is galaxy cluster scale, and it is in galaxy supercluster scale. So what I am going to talk about I am concerned here because my title says that it is Milky Way, and Milky Way is a spiral galaxy. That's why the dark matter in a spiral galaxy, how it behaves and how it is distributed and all, and then only we can talk about the radio waves emission from the possible dark matter. Dark matter has to annihilate actually. I'm telling you here itself. So a little bit of how the dark matter, the existence of dark matter is discovered in a spiral galaxy first. This is long back in 1932. John Hendrik Wood was trying to calculate the velocity of the stars that is going up and down of this spiral galaxy disk. Spiral galaxy means our Milky Way galaxy disk. So going up and down means if you imagine this to be our Milky Way, which is again something like this, which is a spiral galaxy, And it has a disk-like structure with a thickness of 2 kiloparsec. So the stars that is going up and down through that disk, he tries to measure the velocity of those stars. And then what he found, the velocity is much larger than what is expected from the estimation of the luminous part of the galaxies. Luminous part means whatever we can see and whatever we know of, that means dust, stars and all, gas, etc. So then he conjectured and predicted that there must be mass much more than the luminous part of the galaxy in this particular galaxy in our Milky Way, which actually put extra gravitational influence on those stars, and that's why their velocity is much more than what we are calculating from what we are estimating from the luminous part of the galaxy. So that is the first indication that something more is there which is much more than the luminous part of the galaxy, luminous mass of the galaxy. And he actually made a calculation that if that unknown particle, the density should be 2 GeV per cc, which is actually wrong, which is not right for later, but he has made some estimates. The present estimate is 0.3 or 0.4 GeV per cc in the vicinity of the solar system actually. And then Zwicky again. That was in the galactic scale. Now it is in the galaxy cluster scale. So he took Coma cluster and also Virgo cluster, and there he tried to find out the velocities of each galaxies. Inside the galaxy, it is the star velocity. Inside the galaxy cluster, it is the the velocity of the galaxies that he is trying to measure. And then again, he found that it is much more than what is estimated from the visible part of a galaxy cluster, or the visible content of a galaxy cluster. Then he has also made some estimates. He made an estimate that total mass of a galaxy cluster, that is that Coma cluster, will be 400 times more than the visible mass of that particular cluster, which is again faulty calculation. It is around 50, I think. It is around 50 times more. So then again, he conjectured that this unknown particle with mass, whatever, the massive thing that we cannot see, is there in the galaxy clusters also. And supercluster I am not describing here because that will take all the time. But coming back to the galactic scale, the more prolific and more strong evidence of the existence of dark matter came from Professor Mrs. Vera Rubin, who unfortunately demised last year actually. So what she was doing, she actually measuring the radial velocity of the stars in the Milky Way or other spiral galaxies also. What is the radial velocity? It is the velocity of a star at a distance r from the center of the galaxy, which is of course rotating around the galactic center. Now, for that, and she was sampling the stars from near the galactic center and radially outwards. So expected, and she plotted actually this VR, the radial velocity versus the distance r of that particular star from the center of the galaxy. So now expected is this plot will go up initially, and then as r increases, that means the distant stars, they will have a Keplerian fall for their radial velocity. And this of course can be done. Of course there are rigorous calculation for that, but back of the envelope calculation, one can understand the nature of this plot. Sorry, this is again the plot in a bigger way. So what should have happened? First rise, this VR should rise first, and then it will fall down, which is called the Keplerian decline as 1 by root over r. But instead, what he found that this is going up and up and tends to reach a plateau type. So what does that mean? This means the following. This means that what I was saying, just back of the envelope calculation. So this is the star is going round. This is the centripetal force, mv square by r should be equal to gmm by r square. Now, near the center of the galaxy, the star concentration is much more. So this mr is the mass within the radius r. So here near the center of the galaxy, you change mr to 4/3 pi r cube rho and put it there. So near the center of the galaxy, Vr should be of the order of r, and which of course what is found. So Vr goes as r, right? Then what will happen at the distant from this is the galaxy actually. From the galactic center, if you go far, then you will see you can approximate the central part as a part with a constant mass, and then in that case your mr is should be a constant, and then you see Vr goes as 1 by r, 1 by r to the power half, which is the Keplerian decline. So in the normal case, you should have expected going up Vr goes as r, then r to the power half. But since you are getting this Vr is as a plateau, as a constant, that means what? That means you put Vr constant in that this thing formula. Mr is constant. Mr is not constant, of course, and then you find that Mr goes as r. That means as you proceed along r, there is enormous mass present here. This means that this comes from this plot actually, right? Because this plot shows that experimental, observational evidence shows that this Vr tends to goes as plateau. That means Vr is constant. So if you put Vr constant, you will get Mr goes as r. Mr goes as r means it indicates that enormous presence of mass in the galaxy beyond the visible reach of the galaxy, right? So now this means what? This means this. This means that our spiral galaxy or Milky Way galaxy, which is here, it is surrounded by a halo of dark matter. This is surrounded by a halo of dark matter actually. And this extends far beyond the visible reaches of the Milky Way galaxy, or for that matter, any spiral galaxy. And this actually one estimates that our galaxy is 30 kiloparsec from end to end, but this halo can be 200 to 300 megaparsec. So this big halo, spherical halo, is just at the middle of our galaxy sitting, and for that matter, any spiral galaxy, the same nature they exhibit. Okay, so there are other distinct evidence also, which is known as the gravitational lensing. Gravitational lensing is what? It acts as a, you know this, due to gravity, the light takes, bends. This is not very proper to say that light bends. Actually, light rays will follow the geodesic. Geodesic is now curved because of the presence of this very massive object here, right? And then when it follows the geodesic, because the space-time is curved, light follows geodesic, and it follows a curved path. But in the effect, it gives a lensing effect, just like the convex lens. And now you see what will happen. This is a more clearer picture. This is Earth you are observing. You are observing some galaxy cluster here, and again, each galaxy here has a dark matter halo, and all this halo put together gives a bigger halo for the galaxy cluster. So this is a bigger halo of dark matter of the galaxy cluster. Now, say for instance, another galaxy sitting at the background and the opposite side of this galaxy cluster of your line of sight. Now what will happen? You cannot see that galaxy, that blue galaxy there, which is at the background, but because of the distortion of space-time, because of the presence of this huge dark matter halo here, those lights will be bent. And what you will see, you cannot see that galaxy, but you will see the images of those galaxies, because this is a spherical halo, and what you will see the image, that means a circle that is a circle which is called the Newton's ring, Einstein's ring or Newton's ring, Einstein's ring of the images of this galaxy around this galaxy cluster. And that is how actually from this lensing effect, people try to map the dark matter halo, because dark matter cannot be seen, so they try to map how much halo is there from this lensing background galaxy. So you see, this is a real-time picture actually. You see some background galaxies there. This is the galaxy cluster and these are halos, dark matter halos are there. And these are the images of those of a background galaxy which is sort of forms a circle, right? Okay, excuse me for a second. ঠিক আছে. Yeah. So that is called some weak lensing or strong lensing. I'm not going into details of that, but this is micro lensing. Micro lensing is again an interesting thing. Say for instance, a clump of dark matter is floating around in the sky somewhere and you are observing a star. Say for instance, you are observing a star and that clump of dark matter happens to pass by through your line of sight. And if you happen to be at the focal point of the lens that will be produced by the clump of dark matter, then what you will see, that as the dark matter clump passes by your line of sight, the star's brightness suddenly increases because you are at the focus, if you happen to be at the focus. Then when that clump passes away, then again the star gets back its previous brightness. So this type of thing are called the microlensing, and there are a lot of many such observations are made where this microlensing they have seen, and that means from that they conjecture maybe at least some part of dark matter can remain clumped and they are floating around, and they are called actually MACHOs, massive astrophysical halo objects. Okay. But the final nail that the dark matter exists, and it exists in a very vigorous way, comes from this, what is known as the bullet cluster phenomenon. So what is bullet cluster? Bullet cluster is the collision of two clusters. Now, previously, cluster means galaxy. When I say cluster, I mean to say the galaxy cluster. So previously there was a galaxy cluster like this, there was a galaxy cluster like this. They collide with each other. And the enormity of the impact is such that this is the visible part, this was the visible part of this parent galaxy cluster. When it passes through this galaxy, because this is a bigger galaxy, the visible part of that galaxy took a bullet type shape, this type of shape. But here, this is the visible part of the other galaxy, galaxy cluster, but here that much of distortion is not there because their size, because of this size. Now this is the dark matter halo of each cluster. Now you see, this cluster passes to this cluster and goes away. This remains undistorted, this remains undistorted, but the visible part gets distorted. This again shows that the dark matter has very less interaction or no interaction with other particles. But you may say that they have gravitational interaction, that also come into effect, right? Yes, that is true, but the density is so low and they are so scattered away that the effect of gravity doesn't do much to the purpose of their distortion and all. So this I am just going through the next slides very fast because this shows what I just described. Actually, this bullet cluster here, only you see this is just the halo part. The halo part one knows by lensing again. The halo part goes in this direction, undistorted, spherical, but this part, visible gas part, takes a bullet type of shape, and they are going apart. So, and this is the halo part, which is sort of more or less undistorted. So, okay. Now, I will, I am sure you have seen in a lot of places in Google also it is there. this evolution history of the universe, know it pretty well. But why I am showing this, I wanted to tell something about the period when the dark matter could have been created during the process of evolution of the universe. So first one, it starts from a Big Bang, we all know. Then it has undergone a very fast inflationary phase of exponential phase of expansion. After that, particles started creating after the preheating of the inflation and all. This cosmological chronology I don't want to explain here because no time also for that. But when the particles are being created and they are going in thermal equilibrium with the rest of the plasma of the universe, then there is a possibility that dark matter also was created. Dark matter could have been created in other ways also. There are other possibilities theoretically that dark matter could have been created. But most common way, if you think, dark matter could have been created by the annihilation of the known particles. Known particles means what I have shown, quark, leptons, etc., etc. So they annihilate, produce the dark matter particles. And again, the dark matter particles, again, they can annihilate and come back to produce the known particles. That is there also. So it is a more clearer picture. So Big Bang, inflation, then this is the gut stage. I mean, okay, I am not. This is some stage when after inflation, the particles started coming. First is all this thing, radiation, photons, etc. there. So universe was radiation dominated. Then when the matter or particles came into being, then it becomes matter dominated, and then of course nucleosynthesis starts. Nucleus are produced. The nuclei captures electron. Atoms are produced. Then the free photons. Then the photons which so far was scattering with the free electrons present. Then no more electrons will be available for these photons to scatter. That is at what time? That is at a time when atoms are produced. Because atoms are produced when the first nuclei are produced, nucleosynthesis, then those nuclei captured electrons in their orbit and atoms are produced. When atoms are produced, then there are no free electrons available for the free photons in the universe already present to scatter with. That means those photons becomes free. And those photons are free streaming from that era till date. And that creates, you know, perhaps, cosmic microwave background radiation. And you may get that, you may get to see that radiation in your old age TV when there is no transmission. The TV screen was all blobs of white things. Those are actually, it is capturing the cosmic background radiation, and that radiation is all over us. Still, that it is all over us, and it also helps us to know much about the early universe, because those cosmic microwave background radiation comes from this era, 300,000 years after the Big Bang. That means it carries with it the footprints of the early universe. So more you study that background, more you know about the stature of the early universe. So why I told this, and here this part comes from this stage. From this stage it is free streaming for this thing, photons, because photons does not have much electrons to scatter with. So they are free streaming till there, and they form a background. At that time, their wavelength was smaller, but as the universe expands, their wavelengths got stretched, and at that particular era, their wavelength is such that it matches with the microwave wavelength. That's why the cosmic microwave background radiation. Okay. I told this because of a particular reason, actually. So this is the same thing. So this one is the, you see, now this is the cosmic microwave background radiation sky. Now, in this, this should be what? This should be isotropic because what? Because the photons are coming all over from, propagating from all over, and photons should be look same in whatever directions you see. That means they should be isotropic and homogeneous, and they are, but there are slight perturbations are there, what they have found from the present observations. And what those perturbations in the cosmic microwave background, what it says, those perturbations are like holes where the particles can gravitate and form some structure. Structure means it can form a star, it can form a galaxy, or it can form some other structures actually. Galaxy is a structure, the star is a kind of structure. So if you want to form a structure, you have to get the particles and collect it in some hole kind of thing. Those holes were there in the early universe, so that the particles could come and got deposited there kind of, and then from there the stars came out, the galaxy came out. So this cosmic microwave background radiation bears with it those footprints of those small pits or perturbations, and if you study those perturbations, you know what amount of particles, what amount of mass is there, what amount of energy is there. So people are just doing that. People are looking at those these small perturbations and then trying to estimate what is the mass of the universe. And this is exactly in this way only they came to the conclusion that 25.6% or whatever 25.7% of the universe's content is dark matter, 4% is only matter, 68.3% dark energy, etc. So that's what, from the CMBR or cosmic background radiation, this is an older, but this didn't change much actually. The dark matter is 26, these pie charts, they could be able to make this pie chart, where this baryonic matter means the known matter, means all lepton, baryon together, in cosmology they call baryonic matter. So all known particles, all these stars, etc., galaxy cluster, groho, nakshatra, niharika, so everything put together is only 4.9%. And dark matter is 26.8%, and more enigmatic, this dark energy is 68.3%. Okay. So now, depending on how it is created, and what is the nature of its particle, they can be divided into this kind of thing. So depending on their thermal history, they can be thermal dark matter or non-thermal dark matter. And thermal dark matter means the dark matter at the early universe were in thermal equilibrium with the rest of the plasma. Thermal equilibrium means what? Two standard model particles, known particles, are scattering or annihilating, producing dark matter, and dark matters again annihilating and producing the standard model particles. This process is going on, and they thermalize, means they come in the sort of same temperature. The dark matter mass is such that it is equivalent to the temperature of the universe, and they follow this Maxwell-Boltzmann distribution kind of thing, the thermal distribution, the dark matter particles. And also they are in chemical equilibrium. Chemical equilibrium means this forward interaction, forward annihilation, fermion and fermion, electron produce dark matter. This is forward reaction. Dark matter annihilates, produce fermion, antifermion. This is the backward reaction. These two rates are same. So this is how, that means they are in thermal equilibrium, means they have to be in chemical equilibrium also. So in the early universe, they were perhaps in thermal and chemical equilibrium with the rest of the particles of the universe. But then universe is expanding, and universe expands in such a way such that if the rate of expansion of the universe becomes more than the rate of this backward reaction with which dark matter annihilates to produce electron, positron, mu1, mu plus, mu minus, etc., standard model particles, this interaction rate, if falls short of the expansion rate of the universe, then what will happen? They cannot come together and annihilate, right? They cannot come together and annihilate. That means those dark matter are there, but they couldn't come together because the rate is falling down than the expansion rate of the universe. Universe is expanding in such a rate that they are going far and far apart. They couldn't come together because their rate is falling down. Now, in this case, what will happen? They will remain as it is. That means they will not interact with each other. They will be the relic of the universe, and that is known as the relic density of the dark matter. And they are not interacting with each other at the moment unless otherwise they are subjected to special conditions. As such, they are in such a far away distributed that they cannot come together and interact with each other unless they are trapped or they are put together in some very gravitating object or something. So this is the thermal dark matter. That means they were produced by inside the plasma. But in the non-thermal dark matter, there was never in this kind of dark matter were never in thermal equilibrium. So how they can be produced? They can be produced from some gravitational effect after inflation, which I cannot go into now. But they produce from zero. They produce from zero, and they perhaps have slight, very little interaction with other particles in the universe. And so with these interactions, they produce from zero and slowly grow, and reaches an equilibrium position. So for thermal dark matter, it is already in equilibrium. When it is becoming relic, they are going out of equilibrium. For non-thermal dark matter, there were nothing but slowly grows and it tends to the equilibrium density. So these are the two very important differences of thermal dark matter and non-thermal dark matter. And then baryonic, non-baryonic. Baryonic dark matter means those dark matter which are known particles. Maybe a black hole can be a dark matter candidate, somebody says, but then again, the density of the black hole falls far short of 26.5%, far short of. So that means the black hole, even though they can be a possible candidate for dark matter, but they cannot account for the whole dark matter in the universe. They fall far short of that. Although they are talking about the primordial black holes can perhaps produce, but that perhaps can account for that 26.5%, but that needs much more careful research. And so non-baryonic dark matter is most likely this is there. I mean, non-baryonic means the kind of particle which we do not know, which may be a fundamental particle, but we do not know that this kind of fundamental particle exists because its manifestation is not there, and one doesn't know what kind of property they follow and all. Non-baryonic dark matter means they are not those leptons, quarks, Higgs, or nothing. I mean something new. Then there are during when they are getting equilibrated or they are going out of equilibrium, becoming relics and all. Depending on the velocity during that time, during their formation of relics. If their velocity is relativistic, then they are hot dark matter because their velocity is much more. And then otherwise it is a cold dark matter, which was a favorite candidate till date, but perhaps it is losing ground fast. And in between cold dark matter and hot dark matter, there can be warm dark matter, which may be a sterile neutrino. I showed you 3 types of neutrinos, but again there can be one other neutrino, which you termed as the 4th type of neutrino, which you can term as a sterile neutrino, and that is required perhaps for giving the neutrino masses, because how the neutrino gets mass one doesn't know. That is again standard model of particle physics cannot say how neutrino gets mass. For that you have to introduce a sterile neutrino thing, then do some other theory. But this sterile neutrino, if it exists, that can be a candidate for warm dark matter. Okay. So this is very briefly, this is a thermal dark matter. When the universe expands, its density is falling, but it is in thermal equilibrium with the universe. But when this interaction rate I told you falls short of the expansion rate of the universe, it goes out of equilibrium. So it freezes here. This is called the freeze out of the dark matter, of the thermal dark matter. So this is the equilibrium line at different, depending on the mass and this cross section, this annihilation cross section of the two dark matter. It is going out of this equilibrium line at different times of the in the expansion history of the universe. So this is for thermal dark matter, but for non-thermal dark matter, you see, it starts from 0 and going up and going towards the equilibrium density. So non-thermal goes towards equilibrium, thermal goes out of equilibrium, but both becomes relic at some point of time. Okay, so now this figure, don't take it as a Feynman diagram or something, just look at it in this way. If you just look at it in this way, it says the scattering of dark matter with a fundamental particle. F means a fermion, say. It can be a proton, neutron, or electron, mu, or whatever. And it is some mediator, okay. Now, it is a scattering, so dark matter is coming, chi means dark matter is coming this way, and is scattered going this way. Now, if you turn this 90 degree anti-clockwise, then what will happen? This two dark matter is coming like this, annihilates and produce two other fermions, right? If you turn it minus 90 degree, then the diagram look like dark matter going, producing two fermion, right? And if you turn this clockwise 90 degree, then what will happen? Fermion going to dark matter. So the last one I told, that is a production channel for dark matter. Just immediate previous, that means when chi dark matter annihilates and produce fermion, and this one is scattering. So this is a beautiful picture by which you can show the diagrammatically the scattering, the annihilation, and the formation or the creation channels of the dark matter. Why I told this? Because I need this channel where chi and chi, two dark matter, annihilates to produce fermion and antifermion. It can be electron and positron, it can be muon and anti-muon. And that is what exactly happens when the dark matter gets trapped in a huge astrophysical object like the galactic center or the solar core or even at the earth core also. And then they can annihilate. As such, they cannot annihilate, right? I told you that they are so far apart, they cannot come together and annihilate and produce the electron-positron pair. But if they are accumulated in a huge gravitating object and they get trapped by the gravity, by the sheer gravity of those massive astrophysical objects, and they accumulate in considerable number, then that annihilation process starts, and then they can again, after the annihilation of the dark matter, they can produce electron, positron, muon, minus muon, etc. So galactic center is a huge object like that, and dark matter are floating around here and there. So it is always possible that they enter in the galactic center region and then they started scattering, losing their velocity, and there is a huge gravity. The velocity falls down and goes down below the escape velocity of the gravitational pull of that astrophysical object. In this case, in our case, it is the galactic center, and then they get trapped. And they are getting trapped over the years, over the crores of years, and then considerable number of dark matter gets accumulated at the galactic center, then this process again started, this annihilation process again started. That means two dark matter can annihilate to produce electron and positron. The moment they will produce electron and positron, there are electron and positrons try to come out of the galactic center, there are magnetic field, they will give synchrotron radiation. That is how you may get radio wave from the annihilation of this dark matter. Okay? So this is the idea. So here I'm just, this is nothing to do with the annihilation of the dark matter. This is something to do with a very interesting thing. I just thought I will tell you this. Perhaps you know this, of course. You see, the dark matter are there in the galactic halo. In the Milky Way, there is a big halo, I told you. So dark matters are moving around there. But they are moving around such a way, there's velocity, all these things are virialized. That means although they are moving around, the sum of the velocity is 0, because otherwise they would have escaped the halo, right? They couldn't have formed the halo. Now, it is there in some equilibrium. And the sun with its family, the solar system, goes around the galactic center, right? So goes around this galactic center. And so this is the galactic plane, sun with its family is going around this galactic center. Now the Earth is moving around the sun, and this ecliptic or the Earth-Sun plane makes an angle 60 degree with the galactic plane, right? Now, Now what will happen if I move and there are all sorts of scattered dark matter, if I move like this, I will get hit by the dark matter wind. That will be an apparent wind as if it is coming from opposite to the direction of my walking, right? I walk and I am hitting the dark matter as if it is coming from the opposite direction. So that's why, so that one is the apparent dark matter. WIMP means weakly interacting massive particle, which is attributed to the cold dark matter actually. So this is dark matter wind, apparently apparent dark matter wind is hitting the earth, right? Now in December, its motion is in this way, and you see this, the component of the velocity, which is in this direction, this is in the same direction with the apparent dark matter wind. So that means it will get hit by the dark matter less in December, and when it comes to the summer equinox, that means in June, then you see this component of the velocity just facing opposite to the apparent direction of the dark matter wind. So this time it is supposed to get more dark matter, supposed to get hit by more dark matter. So if at all someone can detect dark matter over the years, then it will see a modulation over the year of the total detected amount of the dark matter, and that is called the annual modulation. And similar things happen because Earth is also rotating around its own axis, and then you are trying to detect the dark matter at this latitude, and then you put this thing detector there, and you fix the axis as x and z axis. Dark matter hit at some angle here. You measure this angle, but in 12 hours this has rotated like this. Then your x and z has changed. That means the angle in which it is, apparent angle in which it is hitting your detector is also changed. So you are supposed to see an angular variation of the detected dark matter over 12 hours or 24 hours of your detection process. So it is no bearing with our discussion, but I just thought that I will also share this interesting piece of information with you. Now, coming back to, so those things I was telling you, the detection. Indirect detection is what? That means indirectly you detect. Direct detection means dark matter comes and hit you and you detect the dark matter. That is the direct detection. Indirect detection is dark matter is doing something, giving some other product, and that product you are trying to detect. That is indirect detection of dark matter. The one I was telling previously, that it annihilates and produces electron-positron pair, etc., and then you detect this thing, electron-positron, or some effect of that annihilated product, then that surely will be indirect way of detecting dark matter. Now, just now I mentioned that dark matter is floating all around, but if it gets trapped in a very massive object just due to their sheer gravity, and they enter and their velocity falls down to the escape velocity, which can render them out of that gravitational field, then they get trapped. And how they lose their velocity? Because after entering, they start scattering with the particles in that astrophysical object, and they lose velocity. And losing velocity at one point of time, if that velocity goes down to the escape velocity of that gravitational effect of that object, then they get trapped. And if accumulated in huge numbers, then they again annihilate and produce those fermion bar pair. So target could be solar core. This is a massive object. Galactic center, this is again a massive object. And also the dwarf galaxies. What are the dwarf galaxies? Dwarf galaxies are the satellite galaxies of the Milky Way or any other spiral galaxy. They are dwarf galaxies or satellite galaxies are there. Those galaxies have failed to become a proper galaxy. They are small galaxies. Their star formation rate, etc., are different from the actual galaxy. And so those galaxies also rotate around the Milky Way. Those are the satellite galaxies of Milky Way. There also this dark matter can get trapped and again give rise to electron, positron, etc. And like the Milky Way, dwarf galaxies also have their own magnetic field. Like the neutron star also have their magnetic field. They can get trapped in neutron star also. So what will happen in the galactic center, for instance, for the time being, they get trapped and annihilates, and there are annihilates and produce electron, positron. There are magnetic fields around. Those electron, positron are coming out in the magnetic field. They give this thing synchrotron radiation. So other than electron positron, there can be neutrinos also, there can be gamma rays, there can be positron, antipositron, all sorts of things. And people are looking for everything actually. They are looking for neutrinos from the dark matter annihilation at the galactic center, gamma rays. They have got evidence that there are excess of gamma rays coming from the galactic center, which could have come from the dark matter annihilation at the galactic center. There are a lot of people working on, me too, I worked a lot on that. And there are positrons, antiprotons also. This I am just talking about. That also can come from the annihilation of dark matter at the galactic center. And those things can produce a synchrotron radiation, or the positron itself can be detected by some space-based detector, like this AMS detector in the International Space Station. They have found an excess of this thing, positron. Okay, so these positrons, people are thinking that this huge amount of positron can come only from the dark matter annihilation, because they could not find any other source which can produce that kind of this thing, positron excess. So this AMS thing at the International Space Station experiment, they look for this positron, antiprotons, etc. Okay, just give me a minute. Okay, and so this synchrotron radiation I talked about, annihilation, and then fermion bar, and then this from the magnetic field of the galactic center, or from the neutron star, or maybe from the dwarf galaxies. That synchrotron radiation, if that can be detected by this SKA, then there will be a great thing. The SKA actually will detect the dark matter indirectly. So the targets is, as I told, galactic center, dwarf galaxies, galactic halo. In the halo also there can be clump of dark matter there, and there are theories that the dark matter can clump together in the halo itself if the dark matter mass is less than some mass. I am not going to the details of that. And then there are extragalactic things also. Don't look at that. This is now is no more valid actually. So these forces are valid. So we are focusing on the galactic center. So, okay. So this is the kind of diagram I was talking about. This, you see this dark matter, anti-dark matter going to FF bar. It can go to WZ bosons also. It can decay to give secondary electron, positron, or neutrinos or gammas. And so from the dark matter annihilation, you will get directly primary fermions or secondary fermions or gamma, which can be produced from the decay of WZ, etc. Now, you have to calculate what kind of flux it will give if it comes from the galactic center. That means the dark matter annihilates at the galactic center, electron, positron comes out. In the galactic magnetic field, it produces the synchrotron flux, and whether the kind of flux it will produce, whether it is feasible for the SKA to detect or not. So, which I have made one calculation, and then it says that it is very much possible for the SKA to detect this kind of flux that is coming from the dark matter annihilation. So this is the kind of equation one has to solve. I am not going into details of the equation. Only thing, the dark matter information comes here, and the synchrotron, etc., inverse compound, etc., by which electron loses energy comes here, and this equation has to be, so which I solved actually computationally, and for a particular kind of cold dark matter. And so this is the kind of flux one gets. I will not bore you with the nitty-gritties of this flux and all, but this looks like this, and this is well within the sensitivity of the SKA, which gives by this table. I am not dwelling on this table actually, just to show, just to flash that this is possible by the SKA. Okay. Now, okay. Now, I already told about the dwarf galaxies. So this is the dark matter halo. This is the galaxy, and these dwarf galaxies are rotating all around. This is the older photograph. Now it is 44 dwarf galaxies are discovered till date, and these dwarf galaxies also are the sources of dark matter, where they can annihilate and produce electron, positron, and there are magnetic field around this. So those things can come to the SKA. Could be detected. People are working on that also, me too, working on this, and whether SKA can detect the signal from the dark matter annihilation signal from the dwarf galaxies or not. So this is again an interesting thing. I mean, it will look at galactic center, dwarf galaxies, etc. Okay, so now this is the last item I am talking about. This is a new thing. One should do research on this. At least I will definitely look at it in more details. You see the neutron star. You heard about the neutron star a lot. Neutron star, the dark matter can accrete on the neutron star. And if it accretes at the neutron star core, and if it is an asymmetric dark matter, what is asymmetric dark matter? You see, when during the production time, matter and antimatter were produced in the equal amount because it is produced from the this pair annihilation, this thing creation process. Gamma going to E plus E minus or F bar, and then that way the same amount of matter, same amount of antimatter was created. But what we see here, only the super dominance of matter only. There is no antimatter, because if the antimatter would have been present in the equal amount, then this creation wouldn't have been existed, because they all would have annihilated and universe will remain a radiation type actually. So that means somewhere in the past, in the early universe, there are universe has a slightly more affinity towards matter than antimatter. Why it is so? It is being researched, but a concrete answer has not come out. But at least this much is true, that matter gets over antimatter, and then that excess matter remains, and that is responsible for this thing creation. So one can tend to think that dark matter also created in the same way, dark matter, anti-dark matter, but the slight excess of dark matter. So that slight excess remains as dark matter now, and that's why I am using the term asymmetric dark matter. That means the symmetric dark matter, the equal amount of dark matter, anti-dark matter gets annihilated, only the asymmetric part remains, and that is what I am called is asymmetric dark matter. So if asymmetric dark matter is there, then there is no question of annihilation, because the anti-dark matter is not there. This chi bar is not there actually. So if that kind of asymmetric dark matter are there and they gets accreted in the neutron star core, then what will happen? And if it is a bosonic particle, then soon it will be what Debasish told, Bose-Einstein condensation. And once it forms the Bose-Einstein condensation at the core, this bosonic antisymmetric dark matter, they will readily go into, because of their gravitational pull, they will readily tend to become a black hole, and neutron star will be withered away. So everything will be black hole. But then, if there is an repulsive force act between these two dark matter, then what will happen? Then it will prevent it from coagulating. That means it will prevent it from forming the Bose-Einstein condensates and then subsequently going to a black hole. But this core of dark matter will remain inside the neutron star. But from where this repulsive force will come? Repulsive force can come, you can theorize it by imagining a dark sector where the symmetries that are operating in the visible sector, in the standard model, if you are MSc students or PhD students, you know the standard model is guided by SU2 cross U1 symmetry. Similar, a dark sector, if it is there, and there similar symmetry exists, SU2 dark, U1 dark is there, and from that U1 dark, you will get another photon, which is called the dark photon. Because here in the standard model U1, you get this photon, U1 group symmetry, and where in the dark matter, if there is some kind of dark symmetry is there, which is again follows a U1 group, but in the dark sector, then you will again get a photon, but that is a dark photon, right? And if that symmetry gets broken, I am going a little bit this thing more details actually, technical. It is for those who are senior students. Then in this dark U1, if it breaks, then by the Higgs mechanism, then it will get mass. So we will get another massive dark photon, which not only will prevent this Bose-Einstein condensate to form with this kind of asymmetric dark matter, that itself can be a candidate for dark matter, right? That itself can be, so dark photon is now growing very fast as a popular candidate for dark matter these days actually. So now why I told this? I told this because if you have a dark photon like this is the known photon, standard model photon, this is the dark sector photon, then you will get, similar to Compton scattering, a Compton scattering like this, but this gamma has come out as this dark photon, right? And this is a Bremsstrahlung from with a P and N. Here also, here you can get to see a dark photon if it exists. And what will be of our interest, this dark photon can decay into electron-positron because this dark sector U1 dark photon mixes with the standard model dark photon, and the mixed state can give rise to electron-positron because this mixed state contains certain amount of visible dark photon. That dark photon can decay to electron and positron, and this electron and positron again, under the influence of the magnetic field of the neutron star, will give me something, will give me some synchrotron or something else, and that, since SKA is tuned to see the neutron stars and all, one has to see and calculate, which I am sure I will do it actually. This is a very interesting problem, that if the dark photon of this kind exists and the asymmetric dark matter exists, then what kind of synchrotron radiation can come out if it gets accumulated at the core of the neutron star? Okay, so problems are plenty actually. Problems are plenty, and those are all interesting problems, and that one can do using the SKA actually. So with this, I am almost at the end. So this is the end slide, and just to inform you, if you want to see a bit more of dark matter, what I said, you can read this book also. There are a lot of things are there. Okay, so thank you for your questions.
Okay, I'm Ankita Vera from Presidency University. So my question is to explain the ages detection, ages 21 centimeter detection. People talk about milli-charged dark matter.
Yeah.
So what category does it belong?
That's a new category of dark matter people have proposed actually. But there are different schools of thought, right? Milli-charged dark matter is a certain group of people, they are trying to give this kind of charge. I mean, you can also create a milli-charged dark matter, because if you have a U1 dark sector, then U1 gets broken and the dark matter will get a U1 charge, which is like electromagnetic charge, but in the dark sector charge. But since that U1 photon mixes with the electromagnetic photon also, then that charge has got to do something with the visible charge. You understand? Because it is mixed now. Because your photon A and here A prime, they are mixed. So you do this cos theta sin theta minus sin theta cos theta, and then A1 A2, right? This thing rotate. So your A1 now is A cos theta plus A prime sin theta, right? Now this A sin theta part is actually your known this thing photon, right? This A sin theta part, with that you can relate the U1 charge in the dark sector with the U1 charge in the standard model sector actually. U1 charge in the standard model sector is our electric charge actually. And because I am assuming an U1 charge in the dark U1 symmetry in the dark sector, I will have a similar kind of charge. It will not be an electric charge, but I will have a similar kind of charge there. But since I am telling that they mix, this A and A prime mix, these two charges have some mixing actually. That way, the dark matter can acquire some charges actually. You understand?
Can it interact with the primordial magnetic field?
Primordial magnetic field means the Big Bang magnetic field, yeah. Any charged particle will interact with the magnetic field, but which degree, that depends on the strength of the magnetic field and also to some extent the velocity of the charged particle.
With the nanogauss magnetic field, can it interact with the nanogauss magnetic field?
This is microgauss. This is this one is 3 microgauss. I think the Milky Way galactic center. And nanogauss, I am not sure of actually.
Okay. So, sir, you said that neutrinos can be possible candidates for
Yes, definitely. Yeah.
So, since we know that neutrinos now have mass, we already know neutrinos have mass.
Yeah.
So, there is possibility of both left-hand and right-handed neutrinos in nature.
No. Those neutrinos we will not do. You have to have sterile neutrinos. Right-handed neutrinos, so in standard model is not there. So you should not talk about that. Only you talk about the left-handed neutrinos. So left-handed neutrinos being chargeless and very little mass, you can say that it is a dark matter candidate, but then mass is what, less than eV. And if you put together, it is just 0.04% of that 26.5%. It contribute only to 0.04%. So it is minuscule. It cannot make up this huge 26.5% dark matter in the universe actually.
I'm saying can a right-handed neutrino in principle be a dark matter?
Yeah, if it is a heavy right-handed neutrino, and if you can show with some theory that it exists by some, I mean type 1 seesaw, how it comes I do not know, but it can come with the type 2 seesaw actually, it is or type 3 seesaw, and then you can, yes, of course you can account for that dark matter with the heavy sterile neutrino that has to be. Right-handed neutrino means sterile neutrino it has to be. Yeah.
Also, about this heavy sterile neutrino,
Yeah.
I somehow read somewhere that it should give some 7 kilo electron volt to some X-rays signal. So how?
No. 7 keV X-rays that you are 3.5 keV X-rays that they have got from that different 74 galaxies. That myself and Anirban did the work without neutrino. Explain the same 3.5 keV. So somebody else, Babu and Mahapatra, I think, Babu and his student, they have done this calculation with the sterile neutrino. We have done with the calculation with the scalar dark matter, with the same. But
What's the idea that how can sterile neutrino give that X-ray? So that
No, sterile neutrino is a dark matter candidate. If it is 7.7 keV neutrino, that decays into 3.55 keV photons actually. Okay, that's the whole thing. But you see, one thing is there. Neutrino is a neutral particle, right? And it does not undergo any electromagnetic interaction. So directly, primarily, it cannot produce gamma, right? It has to come through a W loop, then gamma. Otherwise, it has to do a SU2 interaction first. Then you have to W loop. Then from this W plus W minus, the gamma comes. It's the secondary gamma actually. That makes it more rare decay. But it is possible that you can do your own.
Okay, let us thank the speaker once again. Okay, so our next session here at 2 p.m. Quastro. So Dr. Anand Hota will demonstrate how to make image, and there will be competitions with that.
So whoever participated yesterday, they can present their images and explanation. But who did not participate yesterday, doesn't matter. You can still learn from their explanation. And we will more focus on the citizen science workshop. After 2 o'clock to 5 o'clock.
So yeah, at 2
And if you can bring your laptop, that is even better. You can discover here itself. That practice session we can do. If you do not have, still you can enjoy the learning part. Looking at the slide presentations and discussions. Okay? See you after lunch.